So we're going to do a quick review of the different distributions we've been looking at here so far. So first one we looked at was sampling distributions. So here we've got some population, it's got n, it's got some mean here, and what we're going to do is from this take all possible samples of 125. So we're just going to generate 1,000 samples at a time. And what happens is if we get all possible samples of 125 out of these 897 in the population, so we take a sample of 125, take the sample mean. All these means can be a new distribution. The distribution will have a mean very close to the population mean. So 56.117 is very close to 56.037. Like we saw back, we did the thing where I've got a population of 5 numbers, 1, 2, 3, 4, 5. They have a mean of 3. If we take all possible samples of 2 out of those 5, and we find the average of all their sample means, it ends up being 3. If we take all possible samples of 3, take the sample means, all the mean of those means is 3. Samples of size 4, the mean of those means is 3. So when we get all possible samples out of the population of a certain size, when we plot that distribution, the mean is going to be the same as the population mean. Okay, so this is kind of our theoretical case. If we know the population and can take all possible samples out of that population, this is what our distribution will look like. We also talked about how between two standard errors above and below the mean would be our have 95% of the data, which is shown this way. So 95% in the middle here. If we take 2 standard errors, that's about 9. So we're going down to about 47 up to about 65, which is what it shows down here. So that's the sampling distribution for a mean. You also could do it for a proportion. So here we have our population has a proportion of 275. We're going to take samples of size 200. So take a sample of size 200, find the sample proportion or the p-hat for each of those, and we can create a distribution there. And what ends up happening is the mean here should mirror the population mean, so 0.274, 0.275. Okay, so those are the sampling distributions. Next thing we did was looked at the bootstrap. And we can do this for a mean. I'm going to take this. So we have this sample of 500. For the bootstrap, what we do is we take that 500 and the sample mean here, 29.11, is going to be our estimate of the population mean. And then what we can do is take, with replacement, all possible samples of 500 from these 500 values. So again, we generate all these samples, and same thing as we saw before. We've got this bell-shaped curve, and this mean here, the bootstrap distribution, is very, very close to the mean of the original sample. And if we're thinking of this sample in terms of the population, which is more practical, we have a sample that looks like the population, so we can let that sample kind of play the role of the population, if you will. And then we can take all these samples of 500, and we get something close to the mean. And again, here we can, with our standard error, we can find a 95% confidence interval. Another thing we can do with the bootstrap is we can find various values. So here's a 99% confidence interval. We could change that 0.95 to 0.99. And there's a roughly a 99% confidence interval. For the true sample mean, we could find a 62% confidence interval. And that looks like that between these values. So we can change up the size of the confidence interval we do. Right? Again, we can also do this for proportion. Our bootstrapping. So here we've got an original sample with a proportion of 0.52. And we can generate all these samples. And the bootstrap distribution gives us something. Here's the mean of 0.52. So it's spot on there. And so again, this bell-shaped curve gives us the bootstrap. And then the last one was for the hypothesis test. So the randomization distribution. So if you're doing a test for a single mean, so for the randomization distribution, so we're testing a hypothesis, and here we can set the null, an alternative, or we can set the null hypothesis. So if the assumption is 98.6, so I'm generating 1,000 samples, what this does is it sets up a distribution based on the assumption of a mean of 98.6. So taking samples of 50 that have a mean of 98.6, the distribution ends up having a mean that's, again, very, very close to the assumed mean. So 98.6 is the assumed mean. Here we've got 98.603, very, very close. And then what we can do here with the randomization distribution is come up with a p-value. So here we've got our sample mean of 98.26, and let's say we were going on the assumption that the alternative hypothesis is mean less than 98.6, so we're looking at left tail. So we're looking over here, and what we can do is, if we click on this value down here, I want to see where 98.26 shows up. Okay, so that's our sample mean. Where does that show up? Well, it's way down here. The p-value is 0.00025. Really, really tiny. So what that p-value again tells us is, given the assumption of 98.6 as the true mean, getting a sample mean this low, 98.26, really, 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 really unlikely. Okay, less than 0.2, it's 0.025%. Okay, not likely at all. So in this case, we would reject our null hypothesis. All right. So we can look at another one. We've got a sample. We're assuming that the mean is 0. We have a sample that has a mean of 0.124. Again, we're going to generate this randomization distribution. So what we're doing is we're taking samples of 50, assuming the mean is 0. The distribution looks like this. Again, the mean of this is very, very, very close to the null hypothesis mean of 0. And then what we can do is say, maybe we think the mean is greater than 0. So we have a right tail, and again we want to find that particular value, 0.124, which is our sample mean. Our p-value is 0.185. Now that's pretty large. Assuming a mean of 0, getting a mean of 0.124 in a sample of 50 is not so unusual. Okay. If we made this a two-tailed test and looked at that particular value. Okay. Again, being that far away is not it's not that extreme. So our p-value is 0.185. If we're looking at a significance level of 0.05 for our hypothesis test, we would, in that case, fail to reject the null hypothesis. Okay, and then again, we can do this for a proportion. Okay, so we can assume, so let's, if we look at a sample here, our null hypothesis is p equals 0.5. This we can change to anything we want. This can be 0.45, it can be whatever we want. When we generate our samples, what ends up happening, we're finding proportions, samples of 120, assuming the proportion is 0.45. This distribution ends up looking like, this mean ends up looking almost identical to the null hypothesis mean. And then what we can do is look at our sample proportion. What does 0.583 look like? Well, that's way out here. P-value, 0.0018. So that's very low. So assuming a proportion of 45%, getting a sample mean of 0.583 is pretty rare, less than 1%. So there we would reject our null hypothesis. Now, given this particular value, what ends up happening is if we change our null, let's say we change our null to P, or true proportion, equals 55%, what are our chances of getting a sample with 58.3%? Well, if we generate samples again, we'll have a mean of this distribution that looks very, very similar to that, so 0.549 in comparison to 0.55. What are our chances of getting a value as high as 0.583? P-value 0.25. Okay, not that unusual at all. Okay, so depending on what our null hypothesis is, p-value is going to change for any particular value. All right, so those are our different distributions that we've looked at thus far.